Yeah, hello and welcome to Equity Education, the chemistry version. And today we're going to be looking at measuring rates of reaction. Now you might want to get comfortable because this is an extremely long one compared to most of the videos. I would suggest that you may want to stop and start this video, maybe put it into half, maybe put it into thirds, but yeah, it's quite long, so we'll get started. Okay, so I'd like you to open up your booklets and we will start. So, measuring the rate of reaction. So the rate of reaction of a chemical reaction measures, in general, the change in concentration over time. Now there are lots of different ways we can measure the rate of reaction, but one of the most accurate is measuring the change in concentration of a reactant. And this means that if we're going to write this formula, we would have change in the concentration of reactants over the time. Okay, so if we look at this equation, our triangle here means change, and our square brackets indicate concentration. So if you see these square brackets, they mean concentration. Our units, so units of rate, so if we just write it up here, our unit for concentration, you should know as mol/dm -3. Our unit for time is s to the -1. Therefore, if I bring this up all onto one line, we have mol/dm -3, s to the -1. Okay, sorry, that should be s to the 1 here. Okay, so moving on. So measuring rates. So the rate of reaction can be determined by measuring the concentration of a reactant at timed intervals throughout an experiment. And after we've done this, we can draw a concentration time graph. And I'm just going to do a quick, whoops, it's not very straight. Let's try again. So, obviously you would be using a ruler. I am not. This axis would be concentration, and our axis down here would be time. And we may plot our results from our experiment, and we get something that looks like this. So this would be a very basic example of a concentration time graph. So if we carry on with this, and then we'll move back to this graph. So the rate of reaction is equal to the gradient of the curve. To calculate the slope of the curve, a tangent line is drawn to the curve at this particular time. So you may notice that obviously this is a curved line. So that means there must be different rates happening at different concentrations throughout this reaction. Therefore, to work out the rate at a particular given time, we have to draw a tangent curve, a tangent line to the curve. So say I want to decide what the rate of reaction is here, I have to draw a tangent line which would go down like here. Okay, it's a bit thick, that one, but you get the idea. Obviously you will be using a ruler. We can then work out the gradient using this tangent line at this particular point. So here is my gradient that I'm calculating. So this would be the gradient for this concentration here. To calculate this, I would use the formula the change in x over the change in y. Pretty straightforward. Yeah? Okay. So, moving on. So, an example measuring the rate for a decrease in concentration of a reactant. Right, so you have this graph here. And we're just going to write on what it's actually showing. So, on this axis, we have the concentration. On this axis, we have the time. And what I would like you to have a go at doing is to calculate the rate of reaction for the following concentrations. Now remember, this is what you have to do with your tangent lines. Okay, so the first one we will do at concentration of 1.5 mole DM minus 3. Second at 1 mole DM minus 3. And third at 0.5 mole DM minus 3. So remember, you'll be looking at the rate of reaction here at 1.5, the rate of reaction here at 1, and the rate of reaction at 0.5, which is about here. Okay, have a go at it, see how you get on, and we'll go through it together when I come back. Okay, welcome back. So hopefully you should have something that looks like this, where you've drawn 3 tangent lines at the varying temperature, at the varying concentration. So at 1.5, 1, and 0.5. My 0.5 one isn't very accurate because I've actually not left enough space on the axis down here. So that's my bad, but you get the general idea of how it should look. So if we look at our rate of reaction for the following, okay, so not sure what happened there. So for the following, so 1.5 mole DM minus 3. So at a concentration of 1.5 mole DM minus 3, we have a time of 25 seconds. Therefore, to work out my rates, I divide 1.5 divided by 12, which gives us a value of 0.6 mole DM minus 3. At 1, I have a value of around 35 seconds. Again, if you get different values, that's okay. Which equals 0.04 mole DM minus 3. And at 0.5, which isn't very accurate at all, it should equal 52.5 seconds, which gives me a value of 0.0198 mole DM minus 3. Oops. It's rate s to the minus 1. So these are my rates. Now you may notice that they're all different, and obviously at the start of the reaction the rate is quicker and it slows down as we get towards the end of the reaction, which sort of makes sense according to collision theory. We're not going to go through that in very much detail because we've already done that. So we can also calculate something else now, and I'm just going to write it down, then we'll talk about what it is. So we can measure the rate decrease of X at each concentration. And it will become apparent why this is important once we've done this calculation. But the way we do this calculation is we have our rate over our concentration of X. So from our previous calculations up here, we've got our rate, which is 0.06. My concentration was 1.5. My rate here was 0.04. My concentration was 1. And here my rate was 0.0198. over my concentration, which is 0.5. And if I do these calculations, I find out that they are all equal to, or nearly equal to, 0.04. And I can plot this as a graph as well. So again, I'm going to do a quick sketch of a graph. Hopefully you'll be using a ruler. So this would be my rate of decay. This would be my concentration of X. And if I plot this graph, I find that I get a straight line. So why is this important? Well, it's important because it describes the relationship between the rate of decay of X and the concentration of X. And it says that as I increase the concentration of X, it is directly proportional to my rate. So I can write that down as the rate is directly proportional to my concentration of X, e.g. if I double the rate, if I double the concentration of X, I double the rate. Therefore, we can say that rate is directly proportional to my concentration of X. Okay, so this will become important later on when we start talking about order of reactions. Now this symbol, this proportional symbol, okay, we don't use it in an equation. However, I can replace it with this, K. And I can call K my proportionality constant. So again, this will be important when we come on to its when we come on to order of reactions and rate equations later. And technically, if you look at here down here, rate equals K to the concentration of X. This is a rate equation, but we'll go through that in more detail in probably about 15 minutes. Okay, so moving on. So measuring the rate of reaction from a concentration time graph. So sulfur dichloride dioxide SO2 Cl2 decomposes to produce sulfur dioxide and chlorine. Write an equation for the above reaction. Then we've got some experiments, and what I'd like you to do is draw a graph of concentration against time from the above data. Then answer the following questions. Calculate the initial rate of reaction and calculate the rate of the reaction after 3000 seconds. Have a go at that, and we'll go through it not in that much detail, but we will go through it when I come back. Okay, hope it went alright. So we'll quickly go through what we can on here. So write an equation for the above reaction. So sulfur dichloride dioxide SO2 Cl2 decomposes to produce sulfur dioxide plus chlorine gas. Okay, check to make sure it's balanced. It is balanced, so we can move on. So in an experiment, the concentration of the reactions was measured over a period of time. Okay, draw a graph of concentration against time for the above data. Now, I can't really do this on the computer, so I'm just going to have to sketch, and hopefully you will have done a much better job than what I am about to do now. So this is my sketch. Yours should look nothing like this. It should, well, the curve should, but you should be using rulers. So here I have my concentration of SO2 Cl2 in mole dm minus 3. Here I have my time in seconds. Now, you should have drawn a graph, and you should have something that sort of looks like this. So, next question was to calculate the initial rate of reaction. So what is the initial rate of reaction? Well, unsurprisingly, it is the rate of reaction at the very start. So when t equals 0. So to calculate this, I need to draw a tangent line from here at 0 down to here. Again, you should be using a ruler. I hope you are. Now, I'm not going to do this calculation, but I can work this calculation out as rate equals the change in x over the change in y. Again, here I can calculate the rate of the reaction after 3000 seconds by drawing a line. So we will say, we'll arbitrarily put this value here as 3000 seconds. So I need to draw a tangent using my ruler, which I don't have. Oops, down here. So here is where I should be drawing this tangent line, which is a terrible attempt. And then I can work out my rate of reaction again by using this formula. Okay, so I hope that makes sense. Obviously it wasn't the best explanation, but that's about as good as I can do with my technical computer skills. So we will move on. So our next example that we're going to go on to is orders of a reaction. So what do we mean by orders of a reaction? So let's have a look at this. I'm going to write a formula, write an equation down. So we're going to have 2N2O5 gas is to 4NO2 gas plus O2 gas. So what information can be deduced from the equation below? Well, we can tell from this equation that N2O5 decomposes to produce nitrogen dioxide and oxygen. We can also tell the molar ratio. So 2 moles of N2O5 will decompose to produce 4 moles of NO2 and 1 mole of oxygen. However, each reactant can affect the rate of a reaction in different ways. This means that the concentration of each reactant can have a significant effect on the rates. And why is that? So why do the concentrations on some reactants affect the rate more than others? Well, it's because that not all reaction pathways are straightforward. Some reaction mechanisms have a slow step and a fast step, as shown below. So if we take this example up here, I can actually draw a reaction mechanism. And a reaction mechanism shows us the individual steps of the molecules going from their reactants to how they form the actual product. So my first step is actually using N2O5. These molecules break up to form NO2 and NO3. My NO2 combines with my NO3 to produce NO, NO2 and O2, and my NO combines with NO3 to produce 2NO2. This all may look a bit complicated. I do have examples on how to make these reaction mechanisms at the end of the lesson. However, the thing to notice is that we've got different pathways. And these different reactions happen at a different speed. And it is the first reaction here, which is the slow reaction. So this means that the concentration of the N2O5 is the main determinant of the rate of the reaction. It doesn't really matter about these two reactions here because they're fast. We only have to look at the slowest reaction, and that will tell us the rate determining step. Okay, so how the concentration of a particular reactant affects the rate of reaction is given the term order of reaction. And then we'll just quickly mention the rate constant again. We have already done this, so we call this K, and this is the proportionality constant, which will have a certain value for a rate equation as long as the temperature and catalyst is not added. Okay, so moving on. So what do we mean by orders of reaction? So there are lots of different types of orders of reaction, but for the purpose of A level, we will only mention or only talk about zero order, first order, and second order, and we'll give some examples. So in my first example, I have 2 moles of ammonia, and they decompose to form nitrogen and hydrogen. Okay, so this is determined experimentally, so we do some experiments, and in these experiments, the experiments indicate that the concentration of ammonia has no effect on the rate of the reaction. So no matter what I do to the concentration, I might double it, I might triple it, I might halve it, the rate of reaction doesn't change. So that means that my rate equation, remember, would have to have K, and technically it would look like this, ammonia with a 0 up here. Well, that means that I can just remove my ammonia. So my rate equation for a 0 order reaction would be rate equals K. For a first order reaction, we'll do another example. So we've already seen this with our reaction mechanism, so we'll use this as an example again. So again, we do some experiments, and our experiments indicate that as the concentration of is doubled, the rate of reaction also doubles. So we can say that the concentration is directly proportional to the rate. This should say rate. Excuse me. Or the rate is directly proportional to the concentration, which means, as we said previously, we can write it like this. So the rate is directly proportional to the concentration, or we can write it as rate equals Kn2O5 with this proportionality constant. Okay, for a second order reaction, so we use this example. Again, this will be conducted through experiments, and experiments indicate that as the concentration of nitrogen dioxide doubles, the rate of reaction increases by a factor of 4. As the concentration triples, the rate of reaction increases by a factor of 9. So what does that mean? Therefore, the rate of reaction depends directly on the square of the concentration. And I can write the rate equation then as rate equals K. So my concentration of NO2, and it's the square up here. E.g., so we'll just do a quick example. So in the first example of the experiment, I have increased the concentration by 2 here, and then I square it, so the rate increases by 4. In the following example, I've tripled the concentration. I again square it here, and the rate has increased by a factor of 9. So these are our rate equations for our zero order, our first order, and our second order. And lastly, okay, so moving on. So the total order of the reaction. Add up the individual orders of a reaction for each reactant. So in my examples up here, we only have one reactant. However, you may have an example or a question where you have more than one reaction. E.g., so if I have X, Y, and Z, X might have an order of 1, Y might have an order of 2, and Z might have an order of 0. So if I was going to put this into a rate equation, my rate would be equal to K, the proportionality constant, times by X and Y squared. I wouldn't include the Z because that is a zero order reaction. And therefore, the total order of reaction is 3. Okay, I hope this is making sense so far. I know it's a little bit tricky, but we'll stick with it. So how do we find, with respect to a particular reactant, what order it is? So how do we do this? And these are questions that you will definitely be asked about in the exams. So we can do this by comparing or analysing the concentrations of each reactant and the initial rate. So comparing the concentrations of each reactant and the initial rate. And there's some tips to work this out, so try to keep all other concentrations of reactants the same, if possible. And the initial rate method is used when a reaction is too slow and therefore would be too time consuming to carry out all the experiments. So you will have a set of experiments that have varying concentrations for the reactants, and this could affect the initial rate. Okay, so we're going to have a go at doing one of these questions together. E.g., so carry out 4 experiments. 4 experiments are carried out using HCl, propanone, and iodine. And you will have to calculate the order of reactions with respect to HCl, propanone, and iodine. Okay, so what do we mean by this? Let's have a look. So, calculate the order of reaction with respect to HCl. I need to choose two experiments where the concentration of HCl changes, and that would tell me how it influences the initial rates. I want to try and keep the concentrations of propanone and iodine the same, because then I know that the only thing which is affecting the initial rate, if it changes, is the concentration of HCl. So if you look at this table, if we look between experiment 1 and 2, the HCl concentration changes, but the concentrations of propanone and iodine don't. And therefore, analysing experiments 1 and 2, so the concentration of HCl between 1 and 2 is halved, while all other reactant concentrations remain the same. And what happens to my initial rate? 10.9 to 5.4, so my initial rate is also halved. The initial rate is also halved. So the concentration of my HCl is directly proportional to the rate, therefore the order of reaction, WRT to HCl is first order. Just as a quick this means with respect to. So from my experiments I can tell that HCl is directly proportional to the rate. The concentration of HCl is directly proportional to the rate, which means that it must be first order with respect to HCl. We could just quickly show that by looking at the two concentrations in the experiment. So my concentrations in experiment 1 and 2, 1.25 and 0.625, which equals 2. And I can also look at my initial rate between these two, which is 10.9 over my concentration 0.625, which also equals 2. Sorry, 10.9 over 5.2, 0.4, which equals 2, or near enough 2. Okay, so remember what we're doing here is the same, and I'll go all the way back up, as what we were looking at we'll get there eventually here. So I've divided my rate by my concentration, and it shows that they're the same value, so it's directly proportional. Now this means, as we've just been discussing there, that this is first order with respect, in this case, to the concentration or X reactants. Hope that makes a bit more sense now. Okay, moving on. Okay, so I'd like you to have a go at doing this one. Yeah, so I'll give you a couple of minutes, have a look at the table, have a go at see if you can fill out these the missing words, and let me know how you get on. Okay. Okay, hope it went all right. So we'll have a go at going through this then. So calculating the order of reaction with respect to propanone. Now we need to find an experiment where we change the concentration of propanone, and ideally we don't change the concentration of HCl and iodine, and we can tell from experiments 1 and 3 this is the case. Therefore, analysing experiments 1 and 3, the concentration of my propanone is halved, while all other reactant concentrations remain the same. The initial rate is also halved. Let's just check to make that's true. 0.5, 0.25 halved, 10.9 to 5.1 halved. Therefore, the concentration of propanone is directly proportional to the rates. Therefore, the order of reaction with respect to propanone is first order or 1. Again, we could do a calculation just to show it. So my concentration of propanone goes from 0.5 to 0.25, 0.5 to 0.25, and I'm just going to write initial rate. The abbreviations go from 10.9 to 5.1, which is about 2. Okay. Right, so moving on. Calculate the order of reaction with respect to iodine. So again, I need to choose an experiment where the iodine concentration changes and the HCl and the propanone concentrations don't change. Let's go back up and look. So I can analyse between experiments. Which experiments can we use? Experiments 1 and experiment 4. So when the iodine concentration is halved, while all other reactant concentrations remain the same, the initial rate does not change. So this is different. Again, if we go back up, I have halved my concentration between experiments 1 and 4. I've kept everything else the same, and the rate hasn't changed. It's remained pretty much the same. Right, so what does that mean? Well, that means that the concentration of iodine does not affect the rate of reaction. Therefore, it is 0 order with respect to iodine. So whatever I've done to the iodine concentration, it hasn't affected the initial rate, which therefore means it is 0 order. So the total order of the reaction is, and the rate equation, so my rate equation would be rate equals K, first order of HCl, first order propanone, and 0 order with iodine, so I don't include that. Therefore, 1 plus 1 equals 2 as the total order of reaction, and here is my rate equation. Okay, I hope this is starting to make a bit more sense. It is a tricky subject, so I'd recommend you going away and doing some practice. Questions. Okay, so moving on. Right, so we're getting very close to finishing. We're not quite, but we're getting there. So, calculating the rate constants and units. So rate constants can have different units, and these different units are depending on what the order of the reaction is or are. So, for example, if we have a look at a zero order reaction, we know that our rate equation will look like this. So my orders for K, which should be pretty obvious, know that my units for rate are mole dm minus 3 to s minus 1, and because it equals K, this is also going to be my units for K. Right, so a nice easy one to start. First order. We know the rate equation looks like this. We're going to have to do a bit of rearranging to get the K on its own. So K equals rate over X. Now I can put these units in here. So mole dm minus 3 is minus 1 over my units, which for concentration is mole dm minus 3. Therefore, these two mole dm minus 3s are going to cancel out. Which means I'm going to be left with units of s to the minus 1. Okay, and lastly, we'll have a look at second order. So rate equals K. I'll just do X and Y. Yeah. So these are two first order reactions that add up to a total order of 2. And I need to rearrange this equation. So rate equals X and Y. Therefore, we now have 2 mole dm minus 3 concentrations on the bottom. We can again cancel this one with this one, but now we're left with s to the minus 1 over mole dm minus 3. So if I bring my mole dm minus 3 up to the top, it's going to equal mole minus 1 dm cubed and s to the minus 1. Okay, so pretty simple if you can do it that way. It can go on to third order as well. I'm not going to give that as an example because that doesn't usually happen, and you've probably got the idea of how to work out these units anyway. Right, so very quickly, so effective temperature and catalyst on the value of K. So an increase in temperature will increase the value of K in general. And we can say that in general an increase in temperature of 10 degrees Celsius will double the rate. And the concentration of reactants will not change. Okay, so this means that if we do a quick example, rate equals K, let's just do an X and a Y. And I'm going to rearrange this so K is on its own. So rate over X and Y. Now I know that if I increase my rate, my temperature, then my rate is going to increase. My concentration is going to stay the same, X and Y. Therefore, I'm dividing a bigger number here by the same number here, which means that my value of K will increase. Hope that makes sense. And just as a side note as well, a catalyst will increase the value of K also. Won't need to go into very much detail about that. There will be a separate video on temperature and catalyst describing it mathematically, but I think we've had enough at the minute, so I'll do a separate video for that. So the rate constant is only fixed, or it's only yeah, we'll say fixed. If the concentration of the reactants is changed, altering the temperature or adding a catalyst will change the value of K. Right, so I haven't gone into very much detail, but as I said, I think we've had enough for the time being, and we've still got one more section left to do. So our last section, and then I promise we're finished. Predicting mechanisms from a rate equation. So it is possible to predict a mechanism for a reaction given the rate equation if these guidelines are followed. So we are going to look at the formula of the equation, chemical equation, NO2 plus CO forms NO plus CO2. And from experimental data, we have worked out that rate equation is second order with respect to NO2. So we can work out a reaction mechanism, or you can have a go at working out a reaction mechanism if you follow these guidelines. Sometimes it is a bit trial and error, but if you stick to these, you should be able to get the correct answer. On a side note, sometimes there is more than one possible reaction mechanism. As long as you follow those rules and you get a different answer to someone else, it still could be correct. Okay, so the first thing that we have to realize is that the reactant or reactants involved in the rate equation must be the slow step or rate determining step. Yep. So this is the reaction which takes the longest time, which then means it will be the rate of reaction. I think we said it previously, I don't know how many hours ago at the very start of this video. So in this example here, my rate equation is rate equals K for nitrogen dioxide squared. So that means I must have in my rate equation my slow step 2 molecules of NO2 reacting together. Yeah? So I'll start with this, my 2 molecules of NO2 reacting together, and I'm doing that because the reactants appear in the rate equation. Okay, and it's squared, so I know that there's 2 of them. And the next point I'm going to do is that I'm trying to form as many of the products as possible in each step. Okay, so my products are NO and CO2. Well, I can't form any carbon dioxide because I've only got NO2 and NO2 here. So I can form one of my products, which is NO, which means I'm left over with NO3. We'll just write that again down here. So I've formed as many products as I can, which is my nitrogen monoxide, and then make sure any intermediate products are used in corresponding steps. So if I go back to the overall equation, there is no NO3 here. So that means my NO3, which I formed here, must be an intermediate product. So I need to make sure that I use this up in my next step. So I must now know that I have an O3 in my second step. And I need to make sure as well that make sure all reactants and products are used in the mechanism along with the corresponding molar ratios. Okay, so in my second step I have NO3. I have to use it here, so I've moved it down to here. I need to make sure, according to this, make sure all reactants and products are used in the mechanism along with the corresponding molar ratios. Well, in my overall equation I have a CO reactant, I have carbon monoxide, so I must use that here. I still need to form, what do I need to form? I still need to form CO2, which is here. Therefore, my product that I need to form is CO2. And the thing which I've got left over would then be NO2. Okay, so this might seem quite complicated, but I'm going to try and make it a bit easier to understand. So we need to make sure that we've used the right or the correct molar ratios for this reaction. So if I add up this reaction here and this reaction here, I should get my overall reaction here. So let's have a go at doing this. So let's do the first reaction. My reactants are NO2 plus NO2. My other reactants down here are CO plus NO3. The products I form up here are NO plus NO3. My products I form here are NO2 plus CO2. So all I've done is take the reactants from the first step and the second step, added them together, and the products from the first and the second step. Now I'm going to cancel out and see what I'm left over with. Okay, so I have two NO2s on this side, I have one NO2 on this side, which must mean that one of these cancels out. Do I have anything else which is the same? Yes, I do. So I have NO3 here and NO3 here. This is an intermediate, so I do need to get rid of this from one of my steps. I think that was number 2. Is that it? I believe it is. So now I should be able to write the overall equation as NO2 plus CO forms NO plus CO2. Is it the same as my overall equation? Luckily it is. Okay, so that's how you form, or you might be able to do a reaction mechanism. All you need to do is make sure you remember these rules. So the first rule, the reactants involved in the rate equation must be the slow step or rate determining step. Usually that step is the first step, especially at A level. Okay, so we'll just stick with it as the first step. Our second rule, try to form as many of the products as possible in each step. Third rule, make sure any intermediate products are used in corresponding steps. And then make sure all reactants and products are used in this mechanism along with the corresponding molar ratios. Add up all your reactants, add up all your products, get the overall equation. Make sure the molar ratios add up. Went through that quite quickly, but I think we've been going for long enough. I hope you've managed to stay awake, I hope you've managed to survive, and I hope that it has been useful as well. So I will see you next time.